Hi, welcome to the Signal Path. In this episode, we're going to take a look at an upcoming product from Signal Hound. This is a PNCS-1. It's a 1 GHz phase noise clock standard. So in principle, it's a really simple unit. The idea is to create a 1 GHz source that is as clean as possible and therefore can be used as a phase noise clock standard. Which means that if I were to connect this to a spectrum analyzer, say, because it is an exceptionally clean source itself, what I would see in measured phase noise would be the phase noise of the instrument and not of this source. So we'll have to take a look and see how clean it actually is and compare it to some of the specifications of some of the best spectrum analyzers in the world. So really the construction is quite simple. As a result of this, all you have is here, you have a port to enter power. This is a 13.5 volt DC power supply which comes with the unit. There is a minor frequency adjustment port here, so you can adjust the frequency just a little bit if you really need to make sure it is 1 GHz. We may take advantage of that and tune it to my rubidium source standard here. And at the output, all we have is a 1 GHz 10 dBm output port, 50 ohm of course. That's it really. There's really nothing else on this other than that. And we're going to take a look at it inside as well after we do some testing with it. Now it would have been nice if there was at least an LED in here that showed, let's say, that it is warmed up and ready and that the output is stable or something like that. And since there is no switch on it, you cannot turn it on and off except for unplugging it. You can't enable and disable the output other than kind of disconnecting it from the power supply. So it'd be nice if it had an output enable and disable function. I understand they're building this down to a cost with only focusing on getting the best phase noise performance. So it's understandable. Of course, it's made in the USA. So there you go. So let's go ahead and take a look at this. And first, let's compare its specification to something that I have in the lab. Now, the best spectrum analyzer I have here in my lab is the MXA-B, which is an X series spectrum analyzer. I've done a full review and teardown of that unit on my website as well, so you can take a look at it. So we're going to compare it with that and compare it with something I don't have in the lab, which is a UXA, ultra high end. And we could also do the same thing with the Roden Schwarz instrument as well. So there it is. So let's take a look and see what it can do. Hook it up to our spectrum analyzer. Now, one other thing I wanted to mention is that because it is a 1 GHz source here, in theory, you don't have to necessarily use it as a phase noise clock standard to test other instruments. This would be an excellent reference signal for ultra high performance ADCs and DACs as well, where you need a 1 GHz reference where the ADC will then derive its time interleaved clock frequencies from 1 GHz, typically multiplied up and then phase shifted, for instance. So that kind of architecture is also possible. So if you want a really clean source, that's another application for it. And anywhere where you would want a very clean source, this would be used. And because it's again 1 GHz, you could multiply it yourself and you could divide it yourself and create a range of different frequencies coming out of this. And we'll try a little bit of that too. Anyway, enough of this. Let's go hook it up to an instrument and see what comes out of it. So what would we expect to measure? I think it's important to establish the differences between these instruments and what kind of phase noise they have. So here's the MXA-B, the instrument that's sitting on the bench. I have its phase noise at 1 GHz written here. The UXA, which is the ultra high-end spectrum analyzer, goes up to 110 GHz from Keysight, the best cleanest phase noise they have. I've also listed here, and the PNCS-1, the phase noise reference from Signal Hound. So we can compare them. Now we have to be a little bit careful here. Of course, the signal generators inside the spectrum analyzer is a different beast altogether than creating a fixed signal. These guys are widely tunable frequency references used for down conversion. There's a very complex PLL built around it. I've talked about this. I've shown block diagrams and discussed various PLL architectures used in these high-end instruments. So it's very different than creating a signal that's fixed in frequency. You can typically get a much, much better phase noise if you don't have to tune anything. And that has to do with how you choose your PLL bandwidth, what kind of reference is available. These are YIG-based, and this is most likely a crystal, but we have to take a look at it. So then, of course, you're going to have a different shape in the PLL response and a totally different phase noise behavior. So let's compare the MXA and the UXA for just a moment. Now, the UXA is significantly better. So let's compare them. So at 10 Hz offset, which is really close to the carrier, we have minus 80 dBc per hertz from MXA and minus 93 dBc per hertz from the UXA. Now, minus 93 dBc per hertz for a spectrum analyzer is really, really good. And generally speaking, at such a close offset to the carrier, your PLL bandwidth, you're essentially completely within the first PLL bandwidth. So you're locked to some kind of a crystal. And therefore, there isn't much of improvement you can get aside from the crystal you actually use. So from that point of view, we don't expect to see much of a difference from a fixed source than a variable one. But as soon as you move away from that, as soon as you hit 100 hertz, 1 kilohertz offset, things begin to be very different. So let's take at 1 kilohertz. So the 1 kilohertz, the MXA is minus 112 dBc per hertz. And at 1 kilohertz, the UXA is minus 127. That's a huge difference. So 15 dBc per hertz of difference between these two instruments at 1 kilohertz offset is massive. And if you need that to characterize phase noise of very good synthesizers, then of course the UXA is what you have to use, or a dedicated phase noise analyzer which does cross correlation, cancellation, and so on. It's a whole other beast altogether. So now let's compare it to the PNCS. At 10 hertz, you can see minus 83 dBc per hertz. There isn't really that much of a difference between the MXA and the PNCS, as I described why. But now at 100 hertz, you have a sharp slope. You're now at minus 120 dBc per hertz. At 100 hertz, you're at minus 100. So you're already 20 dB better, even at 100 hertz offset from the PNCS. At 1 kilohertz, minus 139, minus 112, big difference. And at 10 kilohertz, minus 145. And minus 114. So even compared to the UXA, for example, at 1 kilohertz offset, minus 139, compared to minus 127, you're significantly better than the UXA also. Again, to be expected, a dedicated fixed frequency is going to be better. So if I were to use this instrument and measure phase noise using this instrument, then I'm just going to read these numbers, because as far as the MXA is concerned, the PNCS is an ideal signal source, and its phase noise is so far below the phase noise of the MXA that it's going to be non-dominant at all. These are dBs, of course, so the powers are exponential. So therefore, we should be able to easily measure the curve that represents the internal PLL of the MXA and its performance and its harmonics and everything that is associated with the internal MXA PLL using the PNCS, and that's one of its applications. If I were to use it on the UXA, at very close to carrier, we are going to be measuring the PNCS, but then above that, we're going to switch back to the UXA. So let's go and see if we can actually get these numbers. These are the typical specification I should be getting from the MXA. So we should be able to read these numbers. These are so much cleaner. So at 1 megahertz, minus 151 dBc per hertz, and at 1 megahertz, minus 147 dBc per hertz, or minus 136 dBc per hertz, you can still see the phase noise advantage, even at 1 megahertz offset. All right, here we go. So I have connected the output of the PNCS directly to my spectrum analyzer up here, and you can see the cable going over here, and I'm using a short, good cable so that I don't attenuate the signal very much. And I've already adjusted the spectrum analyzer here to look at the signal from DC to 10 gigahertz. I don't expect to see any harmonics above 10 gigahertz. So let's go ahead and plug it in. Now this instrument puts out 10 dBm, so I have to make sure that my reference is at least at 10 dBm, which I've done to make sure the attenuation is in there. And let's plug it in. And there it is. So let me go ahead and zoom in so we can see a cleaner view of the screen. Okay, here we go. Here's our multiple harmonics and tones that we see coming out of the unit. So the first tone is sitting at 1 gigahertz and at 9.64 dBm, which is really close to where it's supposed to be. It's supposed to be about 10 dBm and expected plus or minus 2 dBm, so it's very close. Now the second harmonic coming out of it is going to be at 2 gigahertz, and it's sitting at about minus 27, minus 28 dBm. Now the tone is at 10, so you got about 38 dBc of harmonic rejection, which is well within the spec. No problem. You got the third harmonic there and some intermodulation harmonics in the middle. But other than that, it looks really good, looks clean. This is what you would expect to see. But of course, the real measurement is going to be the phase noise measurement. So let's go ahead and switch that to phase noise. Here we go. So I've already set this up to measure from 10 hertz offset all the way to 10 megahertz offset. Now, the first time that we're going to do this measurement, of course, you can notice that between 10 hertz to 100 hertz is going to take a lot longer to measure. That's normal. That's how every spectrum analyzer is going to behave. So we're going to wait until, actually, let me put this into continuous mode. There we go. So it's going to continuously measure. So you can see already the shape of the phase noise. Now, the shape of this phase noise is quite different from the shape of the phase noise you would get from the PNCS. And the reason is because this is not the shape of the phase noise of the PNCS, but of the MXA. So what numbers were we expecting to get from the MXA? Well, we can try it out. Let's put the marker at, let's say, let me choose a marker again. And let's put the marker at 10 hertz. So what do we expect at 10 hertz? We were expecting from the spec minus 80 dBc per hertz, and we're getting minus 81 dBc per hertz. So it is exactly what it's supposed to be. Now at 10 hertz, the PNCS itself is supposed to be minus 83. So there is a bit of contribution from the PNCS on this measurement at 10 hertz, but not anymore at higher frequencies. So let's go to 100 hertz. Here's 100 hertz, and we're getting minus 107. And what is the spec of the MXA? Should be typically minus 100. So it's quite a bit better than what it is supposed to be. So at 100 hertz offset, we're getting a very clean source. And from the PNCS, it's supposed to be minus 120. So it's far worse than the PNCS. This is the MXA. I'm a little bit surprised to see the performance is so good at 100 hertz from the MXA. So let's go ahead at 1 kilohertz. We get minus 114. The spec is minus 112. Perfect. And we can continue going to, let's say, go to 100 kilohertz. At 100 kilohertz from the MXA, we expect to get minus 117. It's exactly minus 117. So you can see how they've designed this PLL, and it's a fairly constant phase noise for quite a few decades there, and then it drops off again. And this gives you hints on the design of the multiple stages of the PLL they have, and how many loops they have, and what they lock to what. We've talked about this quite a bit, and I talked about it during the review that I did for this instrument. And if you go to a 1 megahertz offset, we are going to get a minus 134, and the spec is minus 136. It's got a little bit of a jump here, and that's because I have the noise floor extension on, and sometimes the computation is going to give you that. If I turn the noise floor extension off on this, we're going to get a slightly different result here at the end once this low measurement is completed. But other than that, I think it looks really nice, and it's very obvious that this instrument can be clearly used to characterize this. And actually, I still get a little bit of the weird shape here. That's a bit unusual. I don't know why there's a jump. Something interesting going on with the way it's measuring it. But I think I have a fairly good idea now of what the phase noise of the MXA actually looks like. So having said that, let's hook it up to a different instrument, a different spectrum analyzer, so we can get an idea, and then we'll take it apart and see what it looks like on the inside. And here is the Siglent SSA 3032X, which I've also done a full review on Teardown of, and you can see I'm doing exactly the same thing. The 1 gigahertz signal is present in the middle. Now this doesn't have a phase noise analyzer software, but you can still, of course, measure phase noise. There's nothing magical about that. We're looking at the power spectral density beyond the carrier here, and because again the PNCS is so clean, you can reveal the exact shape of the phase noise of the instrument itself, and you can see there is some phase noise peaking here, and it has to do with how they chose their PLL parameters, and perhaps this was the optimum value, and they've chosen to sacrifice some peaking away from the carrier to accomplish that. So here at the 100 kilohertz offset, we are measuring a spectral density of minus 89 dBm per hertz. The power of the carrier is 10, so we're looking at about minus 100 dBc per hertz for the phase noise, which is a couple of dB better than what they spec it at. They spec it at about minus 97 dBc per hertz. So it's really close to the specification, once again showing that we can do this and we can reveal the shape of the PLL directly in there, which is exactly what we want to do this for. Now there's another thing that I wanted to show you for this instrument, is that let's connect it to some kind of a divider. Let's connect it to a divider and take a look at the output of the divider on the oscilloscope, and this can be used for creating different frequency references that you would want to see in the lab and so on. It should be also interesting to see that. And here's the divider that I wanted to use here. Now I picked this up for a couple of dollars from eBay, and as to be expected, it doesn't really work very well. It has two differential inputs. One input I'm terminating into 50 ohms. I have a 20 dB attenuator on the other input because it doesn't really like such a strong signal, 10 dBm coming from the source there. And the output is terminated into my spectrum analyzer, which is 50 ohms. It's supposed to support all these division ratios, 64, 128, and 256, and it turns out it actually only does 64 and 128. It doesn't really work at 256 at all, and the power doesn't look good. It's consuming very little power from my power supply. So if you look over here, sorry about that, there we go. So it is consuming about 6.7 milliamp from my source there, which is not very much if you want to drive 50 ohm directly. So something might be wrong with my divider there. But nonetheless, we can take a look at the screen and see what kind of a signal is being produced. So right now it's dividing by 64, and as you can see, divide by 64, 1000 divided by 64 is about 15.6. So it is indeed doing the division correctly. I can increase the span a little bit, and we can perhaps stop at, let's say, 100 megahertz instead. So you can see some of the other harmonics. Now it's putting out a square wave, so it's to be expected to see all the other harmonics out there too. It's very asymmetric, doesn't really look good at all, as you can tell by the harmonics. So there it is. So it's putting out minus 13.9 dBm, which is also tiny, but we can still measure the phase noise of the signal coming out. Now what do we expect? Well, normally if you were to divide a signal, then the phase noise should improve, assuming that the divider doesn't actually add its own noise. The jitter stays constant, but the phase noise in dBc per hertz should get better. So let's go ahead and see how the instrument behaves with the divided clock ratio. So let's look at the phase noise impact here. Now we would expect for a division ratio of 64 to get 20 log of 64 improvement, which is about 36 dB. Now we're never going to get that because we're still limited by the instrument, and that is valid for close-in phase noise when the phase noise is still correlated. So, but we're getting minus 95, which is better than what we had before, which was minus 80. And again, this tells us something about the architecture of the LO and how it is locked to a lower frequency. But higher than that, we're back to the region where our phase noise is determined by the main LO in the first conversion stage of the instrument. And I don't think below 3 gigahertz that actually changes from the 1 gigahertz phase noise that we were seeing before. Therefore, if I go at a 1 kilohertz offset, I get exactly the same number, even though my carrier is now only 15.62 megahertz and before used to be a gigahertz. So that again tells us some more insight in the way this instrument works. And that's another benefit of this phase noise clock source, is that by doing divisions and multiplications and feeding it to an instrument, you understand how the instrument handles different LO frequencies and how its PLL is architected, which is quite valuable. Now the next thing I want to do is hook it up to my rubidium standard and see what its frequency is coming out of it, and adjust it to get it exactly at 1 gigahertz if it is off, and then find a way to take it apart and take a look at it. And here's a quick measurement of the actual frequency. So you can see 999.9999603. That's in megahertz. So it's pretty close already. It's not that far from 1 gigahertz. So we should be able to adjust it and bring it closer. Now, this is, by the way, the Fluke PM6685R, something I repaired in the lab. It has a rubidium standard inside, so we're making fairly good measurements. So let's go ahead and try and adjust it. And here it is, just a quick adjustment as all that was required to get this dead on at exactly 1 gigahertz. Now, this is, of course, you have to do a long-term measurement. This is not the best way to ensure that it is precisely 1 gigahertz, but it is very, very close. And just to show you, right now the unit is sitting down like this. What I'm going to do is I'm going to turn it to its side, and that, of course, changes the force of the gravity's direction on the crystal that's inside of this. And that should shift this by a little bit. So let's see if we can actually capture that effect directly by turning the unit sideways. Here we go. So let me try that. There we go, putting it on its side. And I'm holding it. There it is. Take a look. And there you go. You can see a tiny, tiny shift from the force of gravity. That's on one direction. And we can try it completely upside down. And we should see a little bit more even. So it is indeed being affected by gravity, and this is a well-established effect, and that people have explored and even cancel out in some scenarios where frequency is extremely important. So I put it back to the right way up now, and it will go back to the frequency it used to have. So it looks good. Let's go ahead and take it apart. I'm sure we all want to see what's going on inside of it. I'm also very eager. So here's what is inside this unit. Now, it's not all surprising. Perhaps a little surprising from the fact that you have a 100 megahertz crystal. I was expecting that they would start with something a little bit higher, maybe 500, but it's probably because they've done their homework and they found out that this oven-controlled crystal oscillator that they have here, including the harmonics required for multiplication, is still going to give you the best phase noise. So this must be a really, really good reference of crystal there. And I know who makes it, but I don't think I'm supposed to talk about that. It might be some kind of a trade secret. But anyway, so this is some kind of crystal oscillator, oven-controlled, very precise, very clean, as to be expected. Now 13.5 volt DC comes in. We've got some voltage regulation happening over here. There's absolutely no DC-DC conversion here. You don't want anything like that. Otherwise, you're going to put all those spurs onto the output, which is, of course, absolutely undesired. This is not going for efficiency. This is going for best phase noise. So they sacrifice efficiency in power conversion to get that. So after some regulation, they pass the voltage forward to another device. I'll talk about that in just a second. And the output 100 megahertz of this oven-controlled crystal comes out on this side as well. This knob over here, this potentiometer, is what I adjusted to get the frequency precise, and that is just controlling the frequency of the 100 megahertz oven-controlled crystal here. Now they take that, they put it through some resistive divider or resistor RC network or RLC network to further attenuate any noise on this. They really, really want to get rid of all the noises, and they put it through an ultra low noise voltage regulator from Analog Devices to further get the noise as much as possible, because this is going to go into all of the amplification stages. Noise from this will get directly up converted, so they have to really take care of that. And they put beads and resistors everywhere just to get further noise reduction from the power supply, which is required. They don't care about efficiency here, of course. So the 100 megahertz goes through a mini circuit doubler, 200 megahertz comes out. Now these doublers are always going to have some conversion loss, so they need 2 amplification stages. You can see the bias network of the amplifiers over here. There's some L at the output and C in series, just typical bias T's, and then some more filtering in between. So we've got 2 amplification stages to get the 200 megahertz signal as high as possible before passing it to this one. Now this is another mini circuit device. This multiplies the frequency by 5, and it has 22 dB of conversion loss, so you're going to have to make that up at some point. Now the output of this is going to have a 1 gigahertz content, is also going to have a ton of other content from whatever's left over from the first doubler and whatever's left over from the 100 megahertz and all the other harmonics before you get to 1 gigahertz. So times 2, 200, times 5, 1 gigahertz. Now to clean that, some of that is cleaned over here, but then they have a what looks like a SAW filter here, which then only selects the 1 gigahertz output. So now at this point you have a fairly small signal. It's definitely not 10 dBm, considering that you had 22 dB of conversion loss just from this component alone. And then of course they go into this. This says photo lab on it, but I think that's just the casing. The actual circuitry inside must be designed by them. And underneath this, they must have some more amplification in order to get to 10 dBm of output power. So the tiny 1 gigahertz filter signal has to get to 10 dBm from here. Again, you can see some bead over here, which is providing the power supply most likely to this, filtered and amplified and very precise and clean, all the stuff that you need to do in order to get a 1 gigahertz signal amplified. So it's not, even though amplifying 1 gigahertz is not so difficult, but to get the phase noise to stay very good throughout this chain with all these different components that are required, that's really where the challenge is. And getting rid of the harmonics down to minus 35 dBc, those are the stuff that is going to be difficult, even though conceptually the circuit looks simple. On the other side, we have nothing, but you can see some of the other footprints or vias for the complex circuitry that's underneath the can. I cannot take that off because it's soldered down. But other than that, it shouldn't be anything surprising under there either. But whatever it is they've done, they've managed to get 100 megahertz out to 1 gigahertz and very nice and clean. So I think it's a really nicely designed unit. And as I said, many kind of applications, hopefully you got an idea of some of the things it can do. And there you have it. I hope you enjoyed this quick look at this unit, and let me know what you're thinking in the comment section. And if you have any other ideas of the different applications this can have, I think it would be nice to couple this with a programmable multiplier and divider at the output, and you have a very flexible frequency generator that has extremely good phase noise. It won't be a full synthesizer, but it would serve a lot of purposes, especially to be used as clock sources for sensitive applications. Well, I hope you enjoyed this. I'll see you next time.